The last thing for today is just going to be a quick bit of theory, all right? So we were talking about this being solving equations. So far, you haven't seen any equations except for the roots thing. Why is this impact thing an equation? Well, what we're going to do is look at equations in general. If we have equations like this, they're a bit of a pain to deal with. So we're going to do one thing every time we have to solve a nonlinear equation. We are not going to deal with two functions. I simply refuse to deal with two functions. I would like one function and a 0. That's what I like. So the first equation can be rewritten as sine of x minus 1/10 of ln of x equals 0. Now we have one function. And that's it. So this is not rocket science. You can do this with every function, every equation anybody gives you. You just shove everything onto the left-hand side by adding and subtracting terms. And you can always make it so one function equals 0. You can always take everything from the right, put it on the left. Doesn't change anything. But it means you've got one function and a 0. Function equals 0. This is fantastic because it turns this, the sine graph intersects with the ln graph. That's really hard to imagine. Well, it turns it into a nonlinear equation solving problem gets turned into a root finding problem. Now we have a function, and we want it to equal 0. So f equals 0, some function, and we are interested in finding just the places where that function equals 0. And that's all we're going to be interested in. We can turn any equation into this form, so we can imagine there is one function, and we're looking for, okay, where's it across the axis? How does that help us? How does that make life easier? Well, it makes our bisection super easy because there's only so many cases. If I have my function going like this, and let's talk about the a coordinate and the b coordinate on the x-axis. These are x's. And I take the midpoint. And so I notice that this is negative for the y value, negative for the y value, and positive. Which interval should I keep if I'm looking for the root? Let's say I had an interval. I know the root's somewhere between a and b. I check the midpoint. It gives me a negative value back. Which interval should I keep? AC or CB? AC. That's it. I want to keep one thing that's positive and one thing that's negative. If I do that, somewhere in between, assuming the function is continuous, I'll cross the axis. I can throw away this part because, well, it's negative on one side and negative on the other. I got no idea if there's a root there. There might be a root there, but I know there's going to be a root somewhere in the middle. So looking for roots makes it really easy to talk about the sign of the function. And am I close on the positive side, close on the negative side? So here we're going to keep AC because A has a positive value and B has a negative value. And there's not that many cases here because the other option would be that it goes like this. We've got A, and let's put B here, and put C in the middle here. I'll have positive, positive, and then negative. Here we're going to keep the CB part because f of A is positive. Let's be clear here. F of A is positive, f of B is negative. F of C is positive, and f of B is negative. One thing that we can notice, we didn't do all 4 cases here, but let's do that again. If we do all 4 cases, one of the things that we notice is a very simple logic that works here. I'm going to plug in, I'm going to have my 2 endpoints. Someone's going to say search between 45 degrees and 85 degrees was our example earlier. We're going to assume someone like you knows enough to at least roughly bracket the root. And then we're going to say, let's check in the middle and see what happens. Well, the logic is going to be, hey, if I get a positive value and the sign of the function value at b is also positive, then I'm going to throw away b and keep c. And notice that same logic works for all of these things. So if I check at c, c has a negative, f of c is negative, f of b is negative. They have the same sign. I'm going to throw away the b, keep the c. When the sign here, the sign at c is positive, but the sign of b is negative, I do the other thing. I'm going to throw away A and keep C. So we're going to be able to check for this algebraic test. If the sine of f of b is equal to the sine of f of a, then replace b with c. Sorry, f of c. b with c. Otherwise, replace a with c. End. If I get a sign match between my c and my b, if they're the same sign, then I throw away the b, keep the c. If it's not that, then my sign must match a instead, and so we're going to keep the c and throw away the a instead. So we're going to throw away the thing that has the same sign. And that logic actually turns out to be really super easy to implement in MATLAB. So here's how we're going to build it. We're going to build a function, which is also going to have a function as an input, which will get a little meta, but that's fine. So we're going to have 4 inputs to our function called bisection. So let's flip to MATLAB, make a new file, start it with that keyword function, and let's have c be our final value here, and it's going to be called bisection with an f, an a, a b. And one thing that we haven't really talked about, which is when do we stop? Well, we're going to keep bisecting, bisecting, bisecting. If you've done Zeno's paradox, you can do that forever in principle, but in practice, we just, if my angle of launch is good to within 0.01 degrees, I'm probably pretty happy with that. That's what the tolerance will specify. How close do my 2 answers have to be, A and B, before I think, yeah, I don't care if it's any finer than that. So we'll see how that plays out as we write the code. We're going to save it, and notice it'll be saved as a file called bisection.m, because that's how MATLAB names its function files. All righty. Now what we're going to do is look for inspiration back at code that we wrote earlier this week. Earlier this week, we wrote this big while loop. Hey, while 2 values differ by less or by more than some amount, we're going to keep doing things. Well, that's exactly what we want here, except we're going to want a tolerance there. So this is loop while a, b are far apart. And we're going to put an end. That's the basic premise here. We're going to cut, we're going to cut, we're going to cut. We're going to keep doing something until a and b are really close together, less than the tolerance away from one another, and then we'll stop. All right. Things we'll need to do that we also had in the last code, I won't flip back, but was actually define c. So find the midpoint. Midpoint c. C is going to be, careful with your logic here, the average. If I add a and b together, divide by 2, I get something halfway in between them. That's where I want my c value to be. MATLAB's actually giving me a little reminder here that the input argument f hasn't been used yet. We haven't used our function yet. So we're going to go and actually we're going to essentially implement what I wrote on the page there in MATLAB. This, bottom right-hand corner. If the sign, and there's actually a function in MATLAB called sign, which says plus or minus. If the sign of f of c is equal to f of b, we're going to build that if statement in. If the sign of, let's put c first, that's the one we just calculated, is equal to the sign of f of b, then that means f of c, f of b have the same sign. Seems a little redundant. Then we can replace b with c. B gets replaced by c. That's the majority of it right there. And if you go back to the pictures, all we're doing is implementing what those pictures said. OK, find this middle point. Find the function value at the middle point. So we're using our function f now. And once we've done it, we check, hey, was it positive or negative? And was that positive or negative the same as the positive negative for b? If it was, throw away b. If it wasn't, then implicitly this means that f of c and f of a have the same sign. And so we're going to replace a with c. A equals c. That's it. I think that might actually be enough right there. Now, the problem with writing a nice function like this is we can't just run it. Because remember, if you try, you're going to get an error. And that error is going to tell you, oh, that there's a syntax error is what it's going to tell you. Somewhere I'm missing a bracket or something. Oh, I think I must be missing one bracket at the end here. There we go. One more bracket. That wasn't the error message I was thinking of. That's the one I was thinking of. Here we go. Not enough input arguments. We have to give MATLAB a function. We have to give MATLAB an A and a B and a tolerance before, remember, bisection's this friend over here in the corner at a kiosk saying, reading his paper, until you come up and say, here are 4 things I'd like you to work on. Can you tell me where the roots are between A and B of the function f to a tolerance tol? And so we haven't given that information. It yells at us. All right. So we want to test this out. Well, I think it makes sense to use what we did before, which was our targeting thing. And we're going to go back to this one here, and we're going to save it as W43. There we go. And what we're going to do is gut pretty much everything out of this whole side here, except for maybe the print. We'll keep the print maybe. All right. OK. So we've taken all the smarts out of this function so far. Out of this is our main script. This is our, hey, I want to find launch angles that land me at 35 meters. We've got all the launch parameters. And now we want to do this bisection thing. So there's a little hierarchy here. I'm going to show it to you once, and then I'll show you why you would do it this way. So we need a function, all right? We need an f. We need something that we can plug in. We're looking for launch angles. So plug in a launch angle and get the distance. Here. This is actually an important ingredient. We want f of theta naught to equal, actually we don't. We want the landing x. A second here. We want the landing x when I set my angle to equal 35. Okay? That's how we set up the targeting as an equation. My landing x is where I land. It depends on theta naught. And I want it to equal 35. But we can't put that into bisection. Bisection doesn't like that format, nor will any other solver. So instead, we're going to write it as landing x of theta naught minus 35 okay, equals 0. That is our function. Everyone's healthy today. Awesome. All right. That is our moving things to the left-hand side and calling it a function equals 0 problem instead of solving some not too complicated equation, but an equation that doesn't have a 0 on the other side. So that's what we're going to solve. And here's how we're going to get the syntax to work for us. So we're going to say f, and here's an ampersand that's going to go in here. It's going to be a function of theta naught, and it's going to be landing x. And now here's where it gets a little bit odd, but we'll work through it. Notice we're being reminded landing x actually has 3 inputs, v naught, y naught, and theta naught. So we have to put all those in, v naught, y naught, and theta naught, and minus 35. So I cannot express how closely what you put on paper mimics what you're putting in the code here. Very, very, very closely. Defines the function f. We want theta naught. That makes us 0. All right. Notice it's a function. We don't know what theta naught is. That's the whole point of having it up front here is it's going to be a function of theta naught. I don't know what it is, but I want someone else to look for it for me. And so we're going to use functions upon functions here. And we're going to say bisection of that function from A to B, which were defined a little bit earlier. And we're going to set it to a tolerance of 0.01 degrees. Pretty reasonable start. And launch angle. Let's call it launch angle. All right. And we'll just take that out for now. All right. So what used to be a whole pile of code is now really just 2 lines of action. Actually, 1 line of action and 1 line of setup. We're going to define a function. This is a mathematical thing that we scribble out on paper first, figure out, oh, landing x minus 35. Landing is where I do land. 35 is where I want to land. So the difference between those, I want that to be 0. And then bisection looks for inputs that make that 0. So I'm going to cross my fingers here and hope this works. We're going to run it. Ha-ha. Yay. It doesn't always work. It's on the first go anyway. It eventually works, but because this, I'm not sure if you all remember way back to Monday, if you were excited by the angle, but 62.41 degrees was exactly what we found on Monday. By doing the manual bisection, trying to think about too far, too close, now we've got something that's abstracted that away, so a bisection thing I can use on any function I like, and a way to define a function that applies to my scenario, which is I would like to land at 35 meters. The combination of those two is now really easy to look at in the code. Once you get used to it, it's easy to understand what each step is doing, and it gives you the right answer. It gives you the answer you're looking for. So that's bisection.